Welcome to the Airmass CSP video tutorial. This is Block 2, Unit 1, about properties of solar radiation. My name is Stefan Wilbert. I'll start with the solar geometry before I come to the components of solar radiation. Then I'll explain the solar spectrum, and at the end of the presentation I'll show you a simple clear sky model. So let's come to solar radiation basics and solar geometry. I'll start with the extraterrestrial irradiance, which can be found at the top of the atmosphere. In the graph, we see the extraterrestrial irradiance in watts per square meter plotted versus the day of the year. We see that the extraterrestrial irradiance varies. This is due to the elliptical orbit of the Earth around the Sun. Although the extraterrestrial irradiance varies, we define the mean value as the solar constant. The value that is defined by WMO is 1367 watts per square meters. Now some words about the solar time. Daily variations of solar radiation are usually described on the basis of true solar time. True solar time is directly connected to the position of the Sun in the sky, seen from a specific location on the Earth. On the other hand, there is the local mean time. This is the time that can be shown by the arms of a watch that move with a constant velocity. Local mean time is the coordinated universal time plus a constant offset corresponding to the longitude of the location. And local mean time is the time on your watch plus a constant offset. True solar time deviates slightly from local mean time. The deviation of solar time from local mean time is caused by different effects. First of all, by the elliptical path of the Earth around the Sun. Kepler's law tells us that the Earth sweeps equal areas in equal times. The velocity of the Earth moving around the Sun in winter is greater than its velocity in the summer. This is because in winter the Earth is closer to the Sun. Here I'm referring to the winter of the Northern Hemisphere. The other reason for this deviation is the tilt of the Earth's axis with respect to the ecliptic plane. In the end, the difference between solar time and local mean time is usually named E. It's expressed by the equation of time. This equation of time is shown in this graph. On the y-axis we have E, this difference, apparent time minus mean time. This is the same as true solar time minus local mean time. And it's plotted versus the day of the year. E, this difference, is shown in red, so this is total. And we also see two curves that show the effect of, first of all, the elliptic path of the Earth around the Sun in green, and in blue we see the effect of the tilt of the Earth's axis of rotation. We also see a yellow box with an approximation for this difference E. So E can be written as 9.87 times the sine of 2b minus 7.53 times the cosine of b minus 1.5 times the sine of b. Here b is 360 degrees times n minus 81 divided by 364, with n the day of the year. In this sketch we can see the most important angles that are used to describe the solar position. We are here, we are on the horizontal ground, and above us there is the zenith. The latitude of our position can be found here. So this is the angle between the vector that goes from our position to the zenith and the plane that is parallel to the equator. Here we see also the vector that heads towards the south. There is the Sun, and there's also the vector going from our position to the Sun. If we now want to show the solar azimuth, we can do so, plotting the angle between the vector that heads to the south and the projection of the solar vector to the plane in which we are, the horizontal ground. In the sketch we can also see the solar elevation. This is this angle, It's the angle between the vector going from our position to the Sun and the projection of this vector to the horizontal ground. I want to explain also the apparent solar position. The apparent solar position is not exactly the true solar position. This is explained in this sketch. So here we see the Earth as the blue circle and the atmosphere as the gray circle. We see the true position of the Sun, which is given by both the green and the black line. And we see the apparent position of the Sun as the red line. If we are here sitting on the ground, we will see the Sun in the apparent position. This position is different from the true position due to atmospheric refraction of the sunlight. The density of the atmosphere and so also the refractive index increases towards the ground. Because of that, the path of the light is bended as shown with this orange arrow. The deviation of the apparent position and the true position of the Sun is exaggerated in this sketch, but we have to consider it for CSP applications. So this means that for CSP applications we have to include air pressure and height for the calculation of the solar position, and we also have to correct for the air mass. The air mass is explained in this slide. The air mass is a unitless value which is proportional to the length of the light's path through the atmosphere. It increases with the solar zenith angle, and the solar zenith angle is 90 degrees minus the solar elevation. In this sketch, our position can be found here on the Earth's surface, and if the Sun is in the zenith, we will have air mass 1. If the solar zenith angle is 70.5 degrees, the air mass is 3. In this graph we see an example for the solar position in Tabernas in Spain for one specific day. On the left y-axis we see the sun height angle in degrees. On the right y-axis we see the azimuth angle in degrees. The x-axis shows the local standard time in hours. So we see the sun height in red and the azimuth in blue. There are many different formulas to calculate the solar position. I wrote down some examples that only deviate slightly from each other and that are very precise. For example, the uncertainty of the annual algorithm is 0.0003 degrees. The examples are also the DIN 5034 part 2 and the Michalski algorithm from the Astronomical Almanac. But I want to warn you, very simple formulas can deviate by more than 1 degree from the examples I wrote down here. And this deviation is too much for CSP applications. Now I want to explain the 3 components of solar radiation: DNI, GHI and DHI. The sky is not black, and therefore we need different components to describe solar radiation. DNI is what is interesting for CSP. DNI is direct normal irradiance. It is an intensity measured in watts per square meters, and it is measured in a plane normal to the beam coming from the center of the Sun. It's an intensity caused by light coming directly from the Sun. And well, I wrote directly from the Sun in quotation marks because usually all measurement instruments have tracking imperfections, and therefore WMO defines the opening angle of 2.5 degrees for DNI measurements. 2.5 degrees are approximately 10 times the angle of the solar disk, and this means that we do not only measure the intensity caused by light coming from the solar disk, but also we measure some intensity caused by light coming from the region around the solar disk. So in other words, this means that DNI includes circumsolar radiation. In this picture we see a photo of the Sun. I now cover the solar disk. The radius of this circle can be calculated using the distance from the Earth to the Sun and the radius of the Sun. So we can calculate that this radius is approximately 0.27 degrees. And now going back to the photo, we see a lot of forward scattered light around the black circle, and this forward scattered light is circumsolar radiation. Here we see the sun shape. The sun shape is defined as the relative radiance as a function of the angular distance from the center of the sun. We see in this part of the curve the solar disk, and in this part of the curve we see the aureole. This part is also called the circumsolar region. It starts at approximately 0.27 degrees and goes to approximately 3 degrees. The sun shape varies a lot, so that's why I depicted two different sun shapes. First of all, a low circumsolar ratio LBL profile, and then also the standard solar scan. Now I want to come to DHI. DHI is diffuse horizontal irradiance. It's also an intensity in watts per square meter that is measured in a horizontal plane. It's an intensity caused by light coming from the upper hemisphere, but excluding light which is coming directly from the sun. As before, I wrote directly from the sun in quotation marks, and again WMO defines the angle of 2.5 degrees that has to be excluded around the sun. DHI is caused by atmospheric scattering. Here we see the GHI. This is global horizontal irradiance, an intensity measured in a horizontal plane, which is caused by light coming from the upper hemisphere. GHI, DHI and DNI are connected to each other. We can connect them using this formula. GHI is DHI plus DNI times the sine of the solar elevation. Now we can see an example from our high precision meteor station. We see the irradiance in watts per square meter plotted versus the time. We see as a red curve the DNI, as a dark red curve the DNI measured with a second paralleliometer. The green curve shows the GHI and the blue curve shows the DHI. Now a few words about the solar spectrum and clear sky models. In this graph we see different solar spectra. On the y-axis, the spectral irradiance in watts per square meter and micrometer is shown. On the x-axis we see the wavelengths in nanometers. There are different curves. The black curve belongs to the extraterrestrial spectral irradiance, so this belongs to Airmass 0. The blue curve belongs to Airmass 1, the green curve to Airmass 2, and the red curve to Airmass 3. All the colored curves are calculated for standard atmospheres and for clear sky conditions. Clear sky conditions mean that there are no clouds. On the left-hand side, we can see an arrow that shows the visible part of the solar spectrum. The light with wavelengths between approximately 380 nanometers and 780 nanometers is visible for our eyes. If we want to understand terrestrial DNI, we can have a look at this sketch. So first we have the radiation at the top of the atmosphere. Then some radiation is absorbed by ozone. Some radiation is Rayleigh scattered and absorbed by air molecules. There's scattering and absorption due to aerosols. Clouds reflect, scatter and absorb radiation, and a water vapor absorbs radiation. And then we see the direct normal irradiance at the ground. All these different influences have to be considered for radiative transfer models. In the case of clear sky models, we only have to look at the part except of clouds. I want to talk now about a simple broadband clear sky model for direct and diffuse irradiance, which was formulated by Bird in 1984. So first we see the equation for DNI. This is the extraterrestrial irradiance I0 times 0.9662 times different transmittances. The different transmittances are abbreviated by tau x, with x meaning the reason for the transmittance. So we see Rayleigh scattering, we see ozone, molecule absorption, water vapor, and aerosol scattering and absorption. This equation describes I atmospheric scattering, which is not the DHI. It can be calculated using I0, the extraterrestrial irradiance, times the cosine of the zenith angle, times 0.79, times different transmittances. Here we see the transmittance caused by ozone, molecule absorption, water vapor, and aerosol absorption. The aerosol scattering appears later in this further factor. We have to multiply by 0.5 times 1 minus the transmittance caused by Rayleigh scattering plus the forward scattering ratio BA times 1 minus the transmittance caused by aerosol scattering, and this is divided by 1 minus the air mass plus the air mass to the power of 1.02. The forward scattering ratio is 1 for all forward scattering, 0.5 for isotropic scattering, and 0 for all backward scattering. We can now use I atmospheric scattering to calculate the GHI. The GHI is given by DNI times the cosine of the zenith angle plus I ATM-SC divided by 1 minus Rg times Rs. Rs stands for the albedo of the sky and Rg stands for the albedo of the ground. This gives you an idea of the different influences that have to be considered in a clear sky model. If we now know DNI and GHI and the solar position, we can also calculate DHI. On this slide, we see results from a clear sky model compared to measurements. On the y-axis, we see the irradiance in watts per square meter, and on the x-axis, we see the solar time in hours. The measurements are shown in blue, the clear sky model results are shown in red. For this calculation, high-quality input parameters were used. The lower curve belongs to the DHI, the curve in the middle to the GHI, and the highest curve belongs to DNI. On this slide, I want to make clear that a clear sky model excludes a very important factor, which is tau clouds. So we see the same equation for the DNI as before, but with the additional factor tau clouds. In the graph, we see DNI plotted versus the hour of the day. And we see different curves belonging to the irradiance at the top of the atmosphere, belonging to this irradiance after the effect of oxygen and CO2, after the additional effect of ozone, Rayleigh scattering, water vapor, and aerosol scattering and absorption. So a clear sky model brings us to the magenta curve. If we now also consider clouds, and in this example this was done as 1 hour averages, we see a significant reduction of DNI if clouds are present. Sometimes the DNI falls to 0 or very low values, and sometimes the clouds are quite thin and we get quite high DNIs, about 500 watts per square meter. So this shows you the actual limit of clear sky models, because clouds have to be considered. So that was what I want to tell you in Block 2, Unit 1. We saw some slides about solar geometry. I talked about the solar spectrum. Then we looked at atmospheric transfer and the different components of solar radiation. And at the end, we also talked about a clear sky model. I want to thank Robert Pitzpan and Carsten Heuer-Klick for the previous versions of this presentation. And I want to thank Fabian Wolfertstetter for reviewing the slides. Of course, I want to thank you for your attention.